Hey everyone, welcome to another session of Ceerazzledazzle Physics. In today's session, guys, we're going to be talking about Faraday's law of induction and the formula: the voltage induced is equal to dn phi over dt, guys. Okay, and before we get going, guys, make sure you hit the like and subscribe button to keep my channel going and keep my content as free as possible. Right, so before we get started on this topic, which is quite difficult, we're going to have a quick revisit on the idea of the generator effect. So, what exactly is the generator effect? Okay, so here, guys, we're going to revisit the generator effect. You've probably covered this lower down the school, but I'm going to go over it one more time. So over here, we hopefully have the idea that we can generate a voltage by moving a bar magnet into a coil. Here I've got four diagrams here. 1, 2, 3, 4. They're all the same thing here. I've got a voltmeter, and as you can see, I've got a coil. I've got a dashed line at the back to show you it's the back of the coil, and obviously the solid line to show you it's the front of the coil here, to give you an idea of perspective in 3 dimensions. So hopefully we can remember that we can induce a voltage, we can generate a voltage by moving a bar magnet near a coil. So I've got 4 diagrams here, but with the first 2, we're just going to split this in half. So just drop a line here. This is if the bar magnet was to enter the coil. So this is on entering the coil. So entry, we'll put down the word entry actually, as the bar magnet moves into the coil over here. So entry. So initially the bar magnet is over here. So here it is, north and south. And if it's not moving, we won't get any voltage. So the voltage is going to be 0 here generated. But if I were to take that same bar magnet and move it into the coil, so right now look, it's closer to the coil right now, north and the south, and it's entering the coil, what will happen is we will get a voltage. So the voltage will be greater than 0. And obviously, let's just say it swings this way. So let's say the voltmeter, let's say it reads a positive value here. So the voltmeter reads a positive value. And obviously, we have now generated a voltage. Hopefully, you can remember that from lower down the school. But then also, if the bar magnet moves into the coil, we generate a voltage. If you were to take a bar magnet, and let's say it's right next to the coil at the start and it's not moving, let's say it's north and south over here, first of all the voltage will be 0 initially. But then if we're going to remove it, so this is upon exit, if you were to take the bar magnet and move it further away from the coil, so let's say it's north and south over here, you've moved the bar magnet away, what will happen is the voltage will also be generated again, but it will be less than 0. So obviously you're going to get a negative voltage here. Easy idea. So if you have the coil, you move the bar magnet into the coil, you generate a voltage. And by moving the bar magnet out of the coil, you generate a voltage as well. But obviously the motion of the bar magnet, if it's entering, the voltage goes one way. If it's exiting, the voltage goes the opposite way. That is the basic idea behind the generator effect for moving bar magnets into coils. Right, that is one example of the generator effect, but now we're going to look at another example. Okay, so in this example, look, it's not the same as before. Before you were moving bar magnets into a coil, but now look what we're doing here. We're going to take a wire and we're going to move it up and down within a uniform magnetic field. So as you can see, I've got my horseshoe magnet here, north and south. There we go, north and south. Imagine that's a bar magnet. I've bent it into position. And first of all, the uniform field is going from north to south across here. That's my uniform field going across. And what's going to happen is this. If you were to take this wire, let's say you were to hold that part of the wire and move it up and down within the field, you're going to generate a voltage. So you are going to move it. So you move the wire. So you move the wire upwards, you would generate a voltage, yes? And then if you move it downwards, you would also generate a voltage. So downwards motion as well. So if you're going to move, so you are going to move wire downwards in this case. You're going to move the wire downwards here. And obviously if you move the wire upwards, what happens is you'll get, let's say, a positive value of the voltage. The voltage will go up to a certain value. But if you move the wire down, obviously that voltage will change direction. So it'll be negative. So the voltage will change direction. Hopefully you can remember these 2 examples of the generator effect. Now we're going to talk about Faraday's law of induction. So what exactly is Faraday's law of induction? Well, it is basically the generator effect, but in a lot more detail. Right, so Faraday's law of induction states the following. It states that the voltage induced in a wire or coil is equal to the rate of change of flux linkage it is experiencing. So it's a lot of words at the start the first time you read it, but the Faraday's law of induction states that the voltage induced, the magnitude of that voltage which you generate, is going to be equal to the rate of change of flux linkage. Right, so we're going to put down the formula first of all, then I'm going to actually define what each of the characters mean. So voltage is equal to dn phi divided by dt. Okay, so just a quick recap. Hopefully you remember that this is obviously going to be the voltage. Yes. N phi, if you've forgotten, this is going to be the flux linkage. The flux linkage. If you're not sure what the word flux linkage means, watch my previous video in which I talk about flux linkage, magnetic flux density and area. I go into that in a bit more detail. And obviously this is going to be the time over here. This is going to be the time. So voltage is equal to dn phi over dt. So the D stands for the change, yes? So it's kind of like delta if you want, yes? So that's not a quantity, that means that it's the change in flux linkage divided by the change in time. That's the reason why we have that here. Okay, now from here we're going to have to just incorporate the magnetic flux density and the area into this equation. Hopefully you can remember that the magnetic flux density B is equal to phi divided by A. Yes, phi divided by A. So now we can plug this into here, so this becomes D N, and then phi is now BA divided by dt over here. That is our next formula over here. So make sure you can just transition from this formula to this one over here. Okay, and don't forget what they all stand for. So N is going to be the number of wires or coils. I'd put wires or coils. Watch my previous video to understand that in detail there. B is going to be the magnetic flux density. B is the magnetic flux density measured in Tesla, and A is going to be the area, everyone. A is going to be the area here. So make sure we're happy with that formula as well. So Faraday's law of induction states that the voltage induced in the wire or coil is equal to the rate of change of flux linkage it is experiencing. And don't forget, voltage is equal to dn phi over dt, and therefore voltage is equal to dnBA divided by dt. And don't forget, this is also with regards to flux linkage and not flux. That's a key point here. You've got to talk about flux linkage. Alright, now guys, we're going to talk about Faraday's law of induction with a couple of examples. So here's the first example. A bar magnet falling through a coil. So we're going to drop a bar magnet through a coil, and as you can see, this is my diagram here. Bar magnet entering the coil. So here's at start, enters, then exits and travels even further. So 4 diagrams, 1, 2, 3, 4. Right, so initially, this is going to be entry once again. So let's drop a line so we can differentiate between the entry and exit right now. Upon entry, we know that, first of all, the bar magnet, let's draw some field lines over here. So there's some field lines going out, not all of them, so there we go. Okay, right. So initially, we've only got 3 lines maybe going through our field. But then as the bar magnet falls through it, we can see that we've got how many lines going through the field? Well, look, we can see that initially there's only 3, let's just call it 3 Weber passing through. But now there's 5, so therefore it's going to 5 Weber passing through. So look, there's a gain of plus 2 Weber. Therefore, there's a change in flux linkage, because as you can see, only 3 lines thread the loop. And then as it moves inwards, guys, what happens is we notice that 5 lines can now enter the loop. There's a change in flux linkage. Obviously, if you don't move the bar magnet, there's no change in flux linkage. It has to be moving in. And then the same thing upon exit then. So let's say upon exit, we know that initially upon exit, 5 lines are going 1, 2, 3, 4, 5. Let's draw 5 magnetic field lines going through. But then upon exit, 1, 2, 3, and look, there's less going through. So there we go. So initially there's 5 Weber. Let's just say 5 Weber of flux passing through it. And then now there's only 3 Weber here. 3 Weber over here. And obviously now, as it's moved downwards, everyone over here, we have lost flux over here. So obviously from here, we've lost flux. So minus 2 Weber as it goes from here. But look, once again, there is still a change in flux linkage. So you still get a voltage induced. So in this one, you get a voltage. Yes, you're right, because of the change in flux linkage. And in this one, you also get a voltage induced as well. Both of them are a voltage being induced here. But one of them will be in one direction, the voltage, and upon exit, it will be in the opposite direction here. So let's say, for example, we were to plot a graph. I'm going to be doing another video about this later on. Let's say we put a graph of voltage against time for this bar magnet drop going through the coil. there is a voltage generated. So the voltage is generated over here. So look, the voltage goes one way, yes? It drops back down as the bar magnet is right in between. So this is the midpoint then. Then upon exit, we will get a voltage in the opposite direction over here. The voltage in the opposite direction. So look, we can see that the graph will just change direction. Don't forget, upon entry, the voltage is generated in one way. Upon exit, the voltage is generated in the opposite way. And so make sure we understand it's going to be positive voltage and negative here. Very similar to what we did before, in which we talked about bar magnet moving into the coil. Yes, the voltage goes one way. Bar magnet exiting the coil, the voltage goes the opposite way. Very similar to what we covered previously in school. Okay, and from here, make sure we can identify that we get a V maximum over here. The reason why we get a greater voltage upon exit is because think about the rate of change of flux. What about the rate of change of flux? Well, upon exit, the bar magnet is traveling faster. So that's the reason why. So it's traveling faster in this case here. So it's faster. So therefore, we get a higher voltage upon exit. So a higher voltage generated upon exit here. That's the reason why we have this. So just labeling parts of the graph. This part is going to be upon entry. And this part of the graph is going to represent upon exit of the coil. So entry of the coil and exit of the coil here. This is going to be one example of Faraday's law of induction, the bar magnet falling through the coil and the voltage being induced. Think about it. Think about this coil itself. The coil itself is experiencing a change in flux linkage. Look, it's gaining flux linkage upon entry, and upon exit, it's losing flux linkage here. So make sure we actually understand that. Faraday's law of induction, example 2. When a wire is being dragged within a uniform magnetic field, we take a wire and drag it within a uniform magnetic field, we will induce a voltage. So let's say we have this wire, let's call this of length L over here, and we're to take this wire and drag it downwards. We'll say we drag it a distance of X in the field. We will get a voltage being induced, so you will actually generate a voltage. And that should make sense because look, previously at the top, we were dragging, look, the wire within the field. That's exactly the same diagram here. So that field is obviously going across here. But now look everyone, we are dragging the wire within the field here and a voltage is induced here. Okay, right, so we're actually going to look at a formula now for this example of Faraday's law of induction. So first of all, we know that the voltage is equal to dN phi over dt. Okay, right, now, phi is obviously BA, which we looked at from before, so dNBA divided by dt over here. Now, look what's changing. So the magnetic flux density is not changing, that's constant into the page, but the area, is the area changing? Well, think about this. As you move the wire downwards, it's going to sweep through this area of a rectangle here. That's the area it's talking about here. So as the wire moves down, it sweeps through that area over here. So therefore, the formula will then become, well, we can first of all pull out the magnetic flux density, that's constant, N is constant, therefore it's the change in area with regards to time. The change in area with regards to time. The area which it's going to sweep through is XL. XL. So therefore it's going to be equal to BN dXL over dt. Yes, happy with this because area is going to be XL. The length is constant, so we can pull that out again. So it's going to be equal to BNL dx by dt. Dx by dt. And what happens if you were to move a distance x divided by time? Well, hopefully we can remember that dx by dt is the same as the velocity. Yes, that's going to be the velocity. So you're right, the voltage induced, this all becomes this. BNL times by the velocity here. There we go. And then for one wire, last of all, for one wire, N is equal to 1. So therefore the voltage induced when a wire is being dragged within a uniform magnetic field, the voltage induced will be equal to BLV, where V is the voltage induced, B is the magnetic flux density, L is the length of wire, and V is the velocity in which you're moving the wire downwards. So we'll just put that down over there. V is equal to velocity of wire. Okay, right, the next example of Faraday's law of induction will be the following. Okay, and the last example of Faraday's law we're going to talk about is going to be reducing the area of a coil within a field. So this one's a bit crazy, and lots of kids don't understand this one here. And let's talk about the area of the circle. Let's call the area of the circle A1, and then the area of the circle is A2 over here. So imagine you had a coil of wire within a constant magnetic field, and if you were to squash that wire, what will happen is you will generate a voltage as well. So a voltage is induced when the area changes as well. So changing the area of a coil within a field induces a voltage. So if you change the area of a coil within a field, you will induce a voltage as well. This one's a bit difficult to see, but we can actually look at the maths here. So let's say voltage is equal to dn phi over dt. Yes? And therefore we also know that is equal to dnba divided by dt over here. Right, now next thing to ask yourself is what's changing? Is it the magnetic flux density or is it the area? Well, it's just the area which is changing here. So therefore we can pull out n is constant, b is constant, therefore be equal to the rate of change of the area with respect to time here. There we go. So look, that's the reason why a voltage is induced, because the area is changing here. You don't need to have the magnetic flux density changing, you can just change the area of the coil within the field and you will induce a voltage. Right, so this is quite a tricky concept to get your head around, but my advice is the following. When considering Faraday's law of induction, just ask yourself a very simple question. Is the magnetic flux density B changing, or is the area changing A? Because don't forget that voltage is equal to dn phi over dt, which is therefore equal to dnba divided by dt. So whenever you're looking at these problems with regards to Faraday's law, just ask yourself, is the magnetic flux density B changing, or is it the area which is changing here? But if either the magnetic flux density in which the coil is experiencing is changing, or the area of the coil is changing, a voltage will be induced over here. Okay, so from here, let's try and do a question tying this all together. Okay, so it's a long question, but we'll try and do it. Here we go. The uniform magnetic field inside an MRI scanner has a flux density of 0.4 Tesla. A patient inside the scanner is wearing a wedding ring. A finger movement can rotate the axis of the ring through an angle of 90 degrees as shown in a diagram. Calculate the average voltage induced in the ring if the diameter of the ring is 20 millimeters and the ring movement is completed in 0.3 seconds. Right, so this is time t is equal to 0. This is time t is equal to 30. We take the ring and we rotate it. That's what we've done here. So we know that voltage is equal to dn phi over dt, rate of change of flux linkage. So therefore it's equal to dnba divided by dt. Okay, so what's changing? The magnetic flux density B is not changing, so therefore we can pull that out. So neither is n. So n is constant, B is constant, therefore dA over dt over here. The rate of change of the area with respect to time. Rate of change of the area with respect to time here. Now, so we can actually look at this. Right, so this is kind of hard to see, but look, right now when the ring is flat, there's no area which is passing through the field. And then when it goes up, there is obviously an area now. So the area initially is 0 over here. Yes, there's nothing. So it's almost as if it's parallel to the field, so there's nothing passing through it. You're assuming that the ring itself is just like completely thin. And then as you rotate it, obviously the area is now the area of the circle. So the area of the circle is going to be pi r squared. The area of the circle is going to be pi r squared. So therefore the area, we know it's going to be pi. We've got a diameter of 20 millimeters. So pi times by d over 2 squared. Okay, now let's plug all the values in. So n, look, it's just one ring here. So n is 1. So n is equal to 1. B is equal to the magnetic flux density 0.4 Tesla. The time is going to be equal to 0.3 seconds, guys. I've got that wrong from before. This will be 0.3 seconds. This one is 0.3 seconds. And the change in area, I'll go from 0 to there. So obviously the area is just going to be from 0 to there. It's going to be just the area of the circle. So therefore it's going to be 1 times by 0.4 times by the area. It's going to be open bracket pi times by diameter over 2, 20 millimeters, convert to meters, 20 times by 10 to the minus 3, d over 2, there we go, diameter squared, there we go, all of that divided by 0.3. What's going to be our voltage, everyone? I'm getting the answer of 0.42 millivolts over here. Okay, excellent stuff. And that's one question in which we look at Faraday's law. And that's it for another session of Ceerazzledazzle Physics. Make sure you hit the like and subscribe button to keep my channel going, and good luck in your studies. Ciao, ciao, and goodbye.